a deep learning system final project, which is side channel power analysis using convolutional neural networks on AES 128 data set. My teammates are Ingrid, Faizan, and me, Arvind Sinha. A basic premises of our project is that although AES 128 being mathematically secure, real hardware implementation of it leaks information through power consumptions. This enables side channel power analysis attacks to recover the secret key. We model this attack as supervised learning problem where the power traces are the inputs and the AES intermediate bytes value are classification targets. Now, the dataset for the dataset, we use power traces collected from real devices running AES 128 with random plain text and keys, ensuring realistic leakage behavior. Experiments are conducted on the MCU ATX Mega CPU 20 through M dataset recorded from a microchip ATX Mega 164 AU microcontroller at 32 Hertz. The methodology over here that we have used for experiments are that we compared three CNN architectures, the three CNN being variant one, a shared CNN, convolutional backbone, followed by per-byte fully connected layers, then variant two with a simpler shared convolutional backbone, but it's it has a per-byte convolutional and fully connected layers, whereas variant 3 is a fully independent CNN architecture for every byte. Now, moving forward to variant 1, variant 1 uses a single shared CNN backbone as stated above to extract feature from power tracers, followed by 16 independent fully connected heads, one for each AES byte. This design assumes that the early leakage features are largely common across bytes, enabling extensive parameter sharing. The shared backbone captures global temporal leakage patterns, while the per byte head provides limited specializations. The results that we got from variant 1 was that it was able to achieve an average per byte validation accuracy of approximately 1.08%, which is around 2.5 times of baseline of 0.39%. The training is stable. The training was stable with smooth convergence on both training and validation losses. These results confirm that the shared backbone learns meaningful leakage features. Moving forward for variant 2, it introduces a partial parameter sharing by combining a shared convolutional backbone with per byte specific convolutional and fully connected layers. Early layer extracted global leakage pattern common across bytes, while the later layer refined the features for each byte individually. This design balances efficiency with specialization. It explicitly evaluates whether controlled byte level refinement improves attack performance. The result for variant 2 was that it was able to achieve a per byte validation accuracy of approximately 1.27, which was around 3 times the baseline random baseline of 0.39. And it had the lowest validation loss among the tested configuration. Training and validation curve remain closely aligned, indicating good generalization. And the added per byte specific convolutional layer allowed the model to capture subtle leakage differences between each bytes. Now, moving forward, my team member Faizan would continue with variant 3.
Okay. The variant 3 model that we built was basically 16 independent scene. And since we had 16 bytes, so what we thought was building one model for each byte could help us deal with those leakages and understand the AES key much better, right? The architecture was similar. It was like convolutional blocks of 64, 12, and 256, and FC of 256, 512, and 256. Similarly, this is the same classification problem of 256 classes. Overall, the results that we found for the variant 3 were the validation accuracy of around 0.8%, almost twice as random chance. So our initial hypothesis or idea of like having independent models for each byte would be leading to the highest accuracy did not turn out to be true, and it was not alone enough to deal with the weak leakages and give us effective AES key patterns. Overall, then we thought, since this was the initial thought process we had of building 3 different models and then combining them into an ensemble. So maybe because each different variant is slightly unique in its own way, so they're able to understand different leakage patterns. So when we combine them, we're able to understand the AES leakages much more and get to and have much more success in getting to the right AES key. So this is the most important part where you're looking at the standalone performance, right? As you can see, the initial performances that we got were different than the ones you see right now for each variants. That is because the initial performances, those were training and validation accuracy measures For per-trace classification, these accuracies that are you seeing these are based on the full key recovery behavior across many traces in the data sets. That's why they're slightly different. These are more based on the AES success key rather than just per-trace classification metric. As you can see, our initial two variant 1 and variant 3 model are almost as close to random chance, and the variant 2 overall per key performance is much more greater, almost 3 times as better as random chance. Since our ensemble model, due to this, our ensemble model is heavily tilted in favor of variant 2. So rather than capturing different aspects of our model and looking at different leakages, our ensemble was heavily tilted in favor of variant 2, so it was not able to provide us much more better insights into the AES key finding. Overall, then we have to compare the overall performances of all our variants and the ensemble model, right? So validation accuracy is not usually the gold standard for testing out SCPA models or SCPA problems, which is more effectiveness is used as the attack effectiveness versus number of traces. The three usual factors that are metrics that are used as the average key, which means the lower the rank, the better the success at one, and how much like fraction of the bytes which can be recovered correctly, as well as the log likelihood gap, which means the separation between the correct key and the best wrong key. As you can see from our average key rank graph, none of our models are able to fall down or reach one, showing all of our models are not able to successfully get to the AES key effectively. Similarly, success at one graph also shows us the flat line of 0%, which means usually if they're able to successfully get to the AES key, the curves would start to rise up. But all three models and our ensemble do not rise up, showing that the AES key success is not really we're able to find. Similarly, our log likelihood gap also tells us that this similar relationship that all of our three models and the best ensemble model were not able to effectively assist us in getting to the AES key. So what does this final overall tell us is the network architecture were used, although on validation accuracies they were almost 3-4 times better than random chance, but the overall success was not we're not able to achieve in getting to the AES key. That was our initial problem and the initial task of our project. So in conclusion, so this gives us a really good baseline on how to improve our model for any future work and overall insight, and our models and our architectures can be improved to get to the successful AES using better leakage handling, better training objective, improving our trace efficiency, designing better ensemble and better different CNNs, as well as testing on stronger and more varied leakage data sets. So we're able to, our CNN, our neural networks are able to understand the leakages much better and lead us to the successful AES key. Thank you so much to everyone for listening to us, and have a really nice night.